Okay, the exam 2 scores were good overall. Let me know if you have any questions about how it was scored, or if you have any questions about the grade that you think you might have gotten cheated out of some points or whatever. Cheated is a strong word, but okay, we can talk about that. Yeah, I always feel bad when I do that, if that makes you feel any better. When I cross out, I feel better when I cross out a low score, and yeah. But yeah, the scores overall were really good.
For last Monday's lecture,
Mm-hmm.
the recording is really short.
Oh yeah, you know what? I must have paused it for you to work on a problem and then not. Oh, thanks. Oh, Ted, I'll bet. There you go. So yeah, I think what happened was I forgot to restart it probably. But all that material is on the next day's class. Yeah, if you look at, that was on Monday. So if you look at the Tuesday class, everything you missed still, that it is missing, will be on there. All right, so we've done a few example problems with Newton's second law. So now and I said Newton's second law is the most important equation in this class. So now we're getting into, you can write it as an equation. We're not really going to think about it that way, but it's the second most important concept in this class is Newton's third law. Newton was super smart. So Newton's third law. And you've heard some version of Newton's third law, I'm sure, before. The way when, like back in those days, I believe it was the 1700s. It might have been the late 1600s, but I think 1700s. When people wrote math, they did it all like in sentences and stuff. It wasn't like equals and stuff. It was all like described, like the change in the altitude of the, it was all written out like that, is equal to. But anyways, with that voice. So Newton's third law, as it was written, is something like this. For every action, there's an equal and opposite reaction. And that's pretty hard to use mathematically. So the way we're going to think about it is this. So for us, for a contact force acting between bodies, let's say A and B, so acting between bodies A and B, if the force on A, and we're talking about this contact force, so this force on A has to be the force from B, is this with a magnitude of R. Then the force on B from A is in the exact opposite direction with that same magnitude R. so going from one body to the other one, the magnitudes stay the same, and the direction gets flipped. The direction's opposite. So for example, if this guy is standing on the scale, and let's say he weighs 50 kilograms, and we want to calculate the force applied to the, what do I want to do here? Applied to the scale by the man Well, we're not given the mass of the scale, but say we knew what that was. Say we knew it was 1 or 2 kilograms or whatever. If we isolated the scale, we still wouldn't be able to calculate that because we'd have, you can try it, you'd end up with 2 variables in the y direction. You only have 1 equation you can use in the y direction. And so the way to do it is we're going to isolate the man. There's the downward force of gravity. That's 50 times 9.81, so 490.5. Then there's this upward force. I'll call this N for normal. And Newton's second law says 0, negative 490.5. Plus 0 n is equal to 50 times the acceleration vector, which is 0. And so you get an x equation that says 0 plus 0 equals 0, and a y equation that says negative 490.5 plus n is equal to 0. And so you can calculate that n is equal to positive 490.5. Oh, by the way, this is something I'm going to do a lot when I use n as a variable for a normal force. I'll do like the fancy n with the shoes and hat. And when I'm doing it for newtons, I'll just leave it plain. Okay. All right, so in other words, the force vector on the man by the scale, we can get that by plugging this value for n into this vector. This is the force on the man by the scale. So plug that into this, and you get 0, 490.5. Or in other words, that's an upward force of 490.5. But that's not what I asked for in this question. I didn't ask for the force on the man by the scale. I asked for the force on the scale by the man. So to get that, we're going to use Newton's third law. So Newton's third law. says the force on the scale by the man. So we're dealing with the same contact force, but now we're talking about the one applied to the opposite body, is in the opposite direction, so down, with a magnitude of 490.5. And if you, to put that in components, that's acting in the negative y direction with a magnitude of 490.5, so that's 0, negative 490.5. It's newtons. Any questions about that? So that's Newton's third law. And yeah.
Do we have to go through all of those steps? Or can you just go, oh, it's 490.5 down, the normal force is
Yeah, you can do that. I think you'd be surprised a little bit at the pitfalls that come up. So it pays to be a little careful with it at first. But definitely that's what you'll do eventually after you've done a few problems, you know. And maybe it'll, you know, for some people it comes more quickly than others for sure. But let's talk about what this means sort of intuitively a little bit, because this is it mathematically, but what does Newton's third law mean? Its meaning is sort of counterintuitive. It sort of goes against your intuition about how physics works. So think of two sort of examples. One, for most people, I think will make a lot of sense. It'll make intuitive sense. It works the way you think of it. So let's say in one, Newton's third law makes sense. In the other, it doesn't. I think it probably goes against pretty much everybody's intuition. It feels wrong. Okay, so the first one. So this is the one where I think it probably, your intuition about Newton's third law makes sense. Okay, so now imagine it's a beautiful fall day and you're out on the soccer field. Are you on a soccer field? You're somewhere with a barbecue. Do they put those on soccer fields? You're barbecuing, but there are some kids playing soccer, okay? And the ball gets by one of the kids and rolls over to you, okay? And you're minding your own business, tending the barbecue, and the kid says, hey, kick that back over here. And you look up, and the kid is 10 yards away, 5 or 10 yards away. Oh, wait. No, this is important for the story. You're barefoot, okay? You're barefoot. You shouldn't barbecue barefoot. But, so the kid says, can you kick the ball back? And you're like, oh, no problem. And you just go, you kick the ball back, right? No problem, right? Everyone would do the same thing. Everyone would kick the ball back. So now imagine the same situation, but the ball rolls over to you, and you hear the kid yell, and you look up, and the kid's 100 yards away, and you're sitting there barefoot with the soccer ball at your feet. Now you have like sort of second thoughts about it, you know? You're like, you sort of grumble to yourself because you're like, I either have to bring the ball to them or I have to kick this ball really hard. And if I kick it hard, it's going to hurt my foot. Okay? And the reason you know that that's going to hurt your foot is because of Newton's third law. To get the ball to go 100 yards across the field, you have to apply a big force to it. If you apply a big force to the ball, you know the ball is going to apply a big force to your foot. Okay? So that's Newton's third law. And in some ways, in our everyday life, we're used to the way it works, you know? So if you kick a soccer ball harder, it hurts. Okay, now here's the one where it doesn't seem like it makes that much sense. Feels wrong. A home run hitter hits a baseball 400 feet. Okay, so now it's a little harder to wrap your head around the fact that the ball is hitting this guy's bat as hard as his bat is hitting the ball. And one of the reasons that it's hard to wrap your head around that is that you'd think if that were the case, at least every once in a while, the big guy with all the muscles would go up and swing the bat, and the ball would stay right there, and the guy would fly 400 yards, you know? At least sometimes. You'd think probably half the time if it was really fair, you know? So why is it that, how can it be that the ball is applying the same force to the bat that the bat's applying to the ball if the hitter just swings right through, you don't notice any it looks like he doesn't even feel it hit, and yet the ball totally changes directions, flies out of the, you know, yep.
Because he has more mass in the ball.
Yeah, that's the biggest part of it. Yep, exactly. So there are really two things going on that make it not a fair competition, you know. Like if you were trying to make it a fair competition between a 250-pound man and a baseball, here are the two things that you'd have to eliminate. So first, the baseball weighs a few ounces, and the man weighs 250 pounds. And so if you apply the same force to a 250-pound thing that you apply to a 2-ounce thing or whatever, which one accelerates more? Yeah, the smaller thing gets a much bigger acceleration. That's Newton's second law. And then on top of that, to make it even, so far what we're describing is a guy hitting a baseball wearing socks on ice or something. But it's not even that fair because he's wearing cleated shoes that are dug into the sand, and so he's anchored to the earth, which weighs even a lot more than he does, you know? And so there's these two big advantages that make the man stay in place and make the ball accelerate. So the ball does hit the bat with the same force as the bat hits the ball. And anybody here who's played baseball or fast-pitch softball has the experience of the ball coming in, you swing, it comes in your hands, and you hit it with your knuckles. And it's a pretty good reminder that the ball's hitting the bat pretty hard. If you've ever had that experience, it's quite unforgettable. Okay, any questions yet about that? I have to do this one tribute to my high school physics teacher, who wasn't like a really that great a physics teacher, but this was the funniest thing I've ever heard in my life. This was like, it was 1989 or something, and Mike Tyson was like a hot young up and coming, like, this guy could be a good boxer, you know? He wasn't like, he hadn't won any titles yet, but he was like knocking everyone out. And my physics teacher was like maybe 60 years old and like really overweight and like not an athletic guy at all. And he's like, but he, talking about Newton's third law, he says, you know, I wish they'd give me the title shot. I wish they'd give me the chance to fight Mike Tyson. Because I guarantee if I could fight Mike Tyson, I could hit him as hard as he hit me. And then he drew some version of this picture here. So this is supposed to be Mike Tyson's arm. This is like supposed to be his face. If I could hit Mike Tyson as hard as he hits me. And it's funny because it's 100% true. So let's think of the free body diagram of the glove and a free body diagram of the deformed face. So there's all this stuff going on over here and over here. I'm going to ignore that. The only thing we care about is the contact force. And the contact force says Mike Tyson applies a force this way of, how many pounds of force do you think? 2,000 pounds? Is that too much? I don't know. 500? 100? 700 pounds of force. Okay, so Newton's third law says the face applies a force of 700 pounds to the glove. And if you had a sensor inside the glove, like everything would check out. You'd measure it. That would be the case. So I guess the other reason it's funny is because it's not a very good boxing strategy to attack someone's fist with your face, you know? The problem is there's a lot of more important stuff inside your face than there is inside your fist. So these two forces are equal and opposite. Okay, so now let's use this in some problems. Let's say we have 3 carts rolling along the ground. This is 1 kilogram, the middle one is 2 kilograms, and this one's 3 kilograms. And there's a force applied to the right of the 1 kilogram cart of 25 newtons. So first, what's the acceleration vector And these things are going to all move together the whole time, so whatever the acceleration is of one of them is the acceleration of all the other ones. And then second, what's the force applied to the 2 kilogram by the 3 kilogram? Okay, so does anyone remember in a problem like this where where the things are all moving together and we're trying to calculate the total acceleration, what do we want to isolate to get the acceleration? This is pretty much always, you're always going to do it the same. Everything. So we'll do a free body diagram of all 3. There's a weight force. The total mass of this system is 1 plus 2 plus 3, so 6 times 9.81 is 58.86. Then there's a force coming up from the ground. That's the pushing contact from the ground. I'll just call that N total, N for normal. And then the only other force on the boundary is the 25 Newton force on the left. Any questions about that free body diagram? What about the forces between the 2 and the 3 and the 1 and the 2 and that kind of stuff? Those don't appear. And actually, now that we have brought up Newton's third law, now you can understand why only the forces at the boundary matter. If you take forces inside the boundary, we're looking for all the forces acting on this body, right? So the force on the 2 by the 3 is a force on this body, but the force on the 3 by the 2 is also on this body, and they're equal and opposite. Well, when you add those two up, they cancel out. And so all of the things inside have a matching force that cancels it out. The only things that don't have canceling forces are the things happening on the boundary and the weight. Okay, so Newton's second law. 25, that's in the positive x direction. So 25, 0. N total is in the positive y direction, so 0 N total. (58.86) is in the negative y direction, so 0 negative 58.86. Yes. And those are equal to the mass of the whole system, that's 6, times the acceleration vector. What do we know about the acceleration of this system? It's all horizontal, yeah. So we're just going to write this as A0. We don't have to worry about the sign. The sign will work out on its own. So the x component says 25 is equal to 6a. And so A is 4.16 repeating. The y component says N total minus 58.86 is equal to 0. Might as well solve that. So we get N total is equal to positive 58.86. we weren't asked for that. That won't come up in the problem. But okay, so we were asked for the acceleration vector. So remember, this is the acceleration vector. We just didn't have a value for a yet. So now we can plug 4.16 in to this vector as a. And we get that the acceleration vector is positive 4.16 repeating 0. Any questions about that part? Okay, so the second part is we want to figure out the force on the 2 by the 3. There are two ways to do this. One uses Newton's third law and one doesn't. I'm going to do it both ways so you can see, we need to get the same thing or they're not really both ways. So the first way I'm going to do it is with no Newton's third law. So I'll do a free body diagram of the 1 and 2 kilogram carts together. There's a weight of 1 plus 2 times 9.81, so 3 times 9.81 is 29.43. There's an upward force from the ground. I'll call that N 1, 2, the normal force on 1 and 2. And now we're just going to keep going around the boundary looking for places where the outside world makes contact with the boundary. If I'm going around counterclockwise, the next place I get is here. Notice that this is where like right here, can you see my cursor? That's where the 3 kilogram cart would be. So there's a pushing contact on the 2 kilogram cart by the 3 kilogram cart. So that's perpendicular to the surface of contact toward the chosen body. I'll call that R for reaction. And then I'll go around over here, and you have the 25 Newton force. So Newton's second law says 25, 0, plus 0, negative 29.43, plus 0, positive N12, plus, now this vector R is pointing in the negative x direction, so that's negative R, 0. And all that's equal to the total mass, 3, times the acceleration that we just calculated. So 4.16 repeating 0. Any questions about that? All right, so the x equation says 25 minus r is equal to 3 times 4.16 repeating. And that is 12.5. Oh no, 12.5 over here. Well, 25 minus r is equal to 12.5. So 25 minus 12.5 is equal to r. So r is equal to 12.5. The y equation, we're not going to use that. We could if we wanted to solve for that normal force. Anybody have any questions about how I found r there? Okay, so the force on 2 by 3 is this. So we just have to plug this value in for r. And we get negative 12.50. Or a force going this way, 12.5 newtons. Okay, that's one way. Here's the other way. This one we'll have to use Newton's third law. So this time I'm going to do a free body diagram of the 3 kilogram cart. There's a weight force of 3 times 9.81, so 29.43. There's a pushing contact. I'll call that N3. And then if I keep going around counterclockwise, I get to this side where this 3 kilogram cart is in contact with the 2. That's a pushing contact, so it's toward the chosen body. And I'll call that R. No other forces appear. That 25 doesn't appear because that's not acting on the boundary. So Newton's second law says R, 0, because it's in that R is in the positive x direction, plus 0, negative 29.43, plus 0, N3, is equal to the mass of the chosen object times its acceleration vector so the x component says R is equal to 12.5 We can ignore the y equation again. Okay, so now this vector here, what does that represent? The force on what by what? That's the force on 3 by 2. And so if we plug this value for r in here, the force on 3 by 2 is 12.50. And the other way you can write that is it's a vector this direction, horizontal, with a magnitude of 12.5. Does that match what we got before? No. So what's wrong? Yeah, so what we have in the other example, we went straight to the force on 2 by 3. And we got, that negative x component. This time we went to the force on 3 by 2. And we got 12.5 moving to the right. What we're asked for is the force on 2 by 3. And so Newton's third law says the force on 2 by 3 is in the opposite direction with the same magnitude. And that's 12.5 in the negative x direction. So if you want to write that in components, that's negative 12.50. Any of those are fine. If I ask for a vector, then you need to either show the direction and the magnitude, or you need to show the components. But that has the same amount of information in it. So now let's do this one. So there's a cart that's rolling along a ledge, and a cable connects over a pulley to another mast that's hanging below. Let's say the one up above is 500 kilograms, and the one hanging down is 1,000 kilograms. And we want to know what's the acceleration vector of the cart. Okay, so this is whenever you see objects that are connected by, I guess it's always going to be connected by a pulley, moving in two different directions, there's this trick that you have to recognize. A trick for these kinds of problems. And that is that those two accelerations, the acceleration of the 500 kilogram cart and the acceleration of the 1,000 kilogram cart, mass, whatever it is, they're not the same vector, right? One is going to be accelerating horizontally and one's going to be accelerating vertically. But they're also not independent of each other. Okay, can you see that? If this one has a big acceleration downwards, this one has to have a big acceleration to the right. And I think the best way to think of it is they just move in lockstep. If you move this one down an inch, this one has to move to the right an inch.
So are the acceleration vectors just flipped?
So the acceleration, the magnitudes of the accelerations are the same. And you have to just think about the direction, because that can change problem to problem. So okay, the acceleration vectors have the same magnitude just different directions. And the way to think about it is just think, you can choose either one as sort of your reference, but let's say that this one is moving in the positive x direction. Which way is this one moving? Negative y direction. Okay? And so if we call the acceleration of this one a0, because we know it's going to be horizontal, we have to call this one 0, negative a. Okay? A positive value for that acceleration in the x direction means a negative value for the acceleration in the y component of that one. So if the acceleration vector of the 500 is a0, then the acceleration vector of the 1,000 is 0, negative a. Okay, so I'm going to start with a free body diagram of the cart. The forces are the weight. So 500 times 9.81 is 4,905. And then there's a pushing force from the ground onto the wheels. I'll call that normal 500. And then there's the force from the cable. You know, I mentioned this before, that I'm sort of in the habit of including just a tiny little bit of that cable in the body that you isolate. Then the force comes out of that stump of cable. So I'll call that T. And there's no other forces acting on this. So Newton's second law says 0, negative 4,905. Plus 0, n500. Plus T0. Is equal to the mass, 500, times the acceleration vector that we're just going to write as a0. And this vector is what we're trying to find. That's the vector a500. Okay, so the x equation says T equals 500a Can we solve that? No. We have one equation, two variables, so you can't go any farther than that. But let's just set that aside as something useful, and we'll come back to it later. Okay, what we're trying to come up with is a system of equations that we can solve. So I'll call this equation 1. The y equation isn't going to help us on this. I'm just going to leave that one alone. If you wanted to calculate that normal force, you could. And now let's go to the hanging mass, so free body diagram of the 1,000. There's the weight. That's 1,000 times 9.81, so 9810. And then the only other place there's contact is where the cable touches it. So we know that cable force acts straight up out of the stump. Do we know anything about its magnitude? We do know one thing. We don't know the number. We know it's the same. We know it's the same as the T that we already named because it's the same cable. All it does is go over pulleys. And so make that T. And now Newton's second law says 0, negative 9810 plus 0t is equal to the mass, 1,000, times the acceleration vector. Now this is where we have to use that relationship between acceleration vectors that we came up with at the beginning. So I'm going to write this acceleration vector as 0, negative a. That vector is a 1,000. The x equation says 0 equals 0, so that doesn't help. The y equation says negative 9810 plus t is equal to negative 1,000a. Can we solve this equation? Yeah, we can't do it by itself because it's one equation with two variables, but what we can do is call this equation 2. And now equation 1 and 2 together are a system of two equations for two variables. The easiest way to do this is substitution. So I'm going to substitute equation 1 into 2. T is equal to 500A, so this combined equation says negative 9810 plus 500A is equal to negative 1,000A. And now we have one equation for one variable, negative 9810. Subtract 500A from both sides, you get negative 1,500A. solve for A. And you get 6.54. So A is equal to positive 6.54 meters per second squared. We were asked for the acceleration vector, so A 500, we'll take this value, plug it back into this vector. And we get 6.540. Any questions about that? Okay, let me give you one to work on, and then maybe I'll just start with this next time. I don't know how long this will take. So let's say that we have 2 carts. On a flat surface. A force is applied to the 1 kilogram cart of 10 newtons pushing to the right, and a force is applied to the 2 kilogram cart of 5 newtons pushing to the left. We want to calculate the acceleration vector, and we want to calculate the force on the 1 by the 2. Okay, so see if you can think through that one, and let me know if you have questions.